In this section, we're looking at a few more sets of trigonometric identities. The first set we're looking at is our double angle formulas. And here we have the sine of 2 times an angle, or 2u, is equal to 2 times the sine of that angle times the cosine of that angle. For cosine of 2u, we have 3 alternatives. First one is cos squared u minus sine squared u, or we have 2 cosine squared u minus 1, or our final alternative is 1 minus 2 sine squared u. For tan of 2u, this is equal to 2 times the tan of u all over 1 minus tan squared u. Here we have an example in which we are trying to find the exact value of the trigonometric function of sine 2 theta and secant of 2 theta given the figure where we have our opposite side is equal to 1 and our adjacent side is equal to 4. From our Pythagorean theorem, we can find our hypotenuse. We know this would be the square root of 4 squared plus 1, so this ends up being the square root of 17. We know sine 2 theta is equal to 2 sine theta cosine theta. So it's just a matter of substituting for sine theta and cosine theta here. So now we have 2 sine theta would be the opposite over the hypotenuse. So this becomes 1 over the square root of 17. And cosine theta would be 4 over the square root of 17. We simplify, so we have 2 times 1 times 4, which is 8. And the square root of 17 times the square root of 17 gives us just 17. So this ends up being 8 over 17. To find the value of secant of 2 theta, we can use the reciprocal identity. We know secant theta is equal to 1 over cosine theta. So this becomes 1 over cosine 2 theta, since we have 2 theta here. We know cosine of 2 theta is cosine squared theta minus sine squared theta from our double angle formula. Now we can substitute for cosine theta and sine theta. So this is 1 over cosine is 4 over square root of 17 squared minus sine, which is 1 over the square root of 17 all squared. This simplifies to give us 1. This is 16 over 17 minus 1 over 17. So this is 1 over 15 17. We find the reciprocal, so this just becomes 17 over 15. So the secant of 2 theta is equal to 17 over 15. Here we're using the same figure to find the exact value of the trig function tan 2 theta and tan 4 theta. We know from our double angle identity that tan of 2 theta is equal to 2 tan theta all over 1 minus tan squared theta. We know from our triangle that tan is equal to 1 over 4, since they're opposite over adjacent. So here we can substitute for tan. So this becomes 2 times 1 over 4 minus 1 minus tan of 1/4 squared. This simplifies to give us 8 over 15. Now here we're finding tan of 4 theta. This can be written as 2 times 2 theta. Now going back to our identity, this becomes 2u. So our u is actually 2 theta. So now we have 2 tan 2 theta all over 1 minus tan squared 2u, or 2 theta. So now we need to find tan of 2 theta, which we have already done. So it's just a matter of substituting for 2 theta. So this becomes 2 times 8 over 15, because 8 over 15 is equal to the tan of 2 theta, all over 1 minus 8 over 15 squared. And this simplifies to give us 240 over 161. Now we'll be looking at a few examples of using our double angle identities to solve equations. In our first example, we have sine of 2x times the sine of x is equal to cosine of x. So here we have our double angle sine of 2x. We know our double angle sine of 2x is equal to 2 sine x cosine x. So this becomes 2 sine x cosine x times sine x. And if we subtract cosine x from both sides, it ends up being negative cosine x on the left side. If we simplify this, we can multiply the sine x by sine x. So this becomes 2 sine x squared times cosine x minus cosine x is equal to 0. From this we can see that cosine x is common to both terms. So we can factor the cosine x. If we factor out cosine x, we're left with 2 sine squared x minus 1. Now this is an equation we can solve using our zero factor property, so we can set cosine x equal to 0 and 2 sine squared x minus 1 is equal to 0. So here we have cosine x is equal to 0. So where cosine x is equal to 0 is at angle pi over 2 and 3 pi over 2 within the interval of 0 to 2 pi. Now we're going to solve 2 sine squared x minus 1 is equal to 0. We add 1 to both sides and divide by 2. We get sine squared x is equal to 1/2. We take the square root of both sides and rationalize the denominator, we get plus or minus the square root of 2 over 2. So where is sine x equal to plus or minus square root of 2 over 2? Pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. So our solutions for this equation is these 6 angles. In this example, we're finding the exact solution of cosine of 2x plus sine x is equal to 0, and in the interval of 0 to 2 pi. Here's our double angle cosine of 2x. We know our double angle identities are cosine of 2x is equal to cosine squared x minus sine squared x, or 2 cosine squared x minus 1, or 1 minus 2 sine squared x. So we're going to replace cosine 2x. We decided to use 1 minus 2 sine squared x because our other trig function is sine. So we're trying to keep all the trig functions to be the same. So now we have 1 minus 2 sine squared x plus sine x. If we rearrange these and factor out the negative 1, this becomes 2 sine squared x minus sine x minus 1 is equal to 0. We can further factor this trinomial. So now we have 2 sine x plus 1 times sine x minus 1 is equal to 0. Now we can use our zero factor property again and set this factor equal to 0. So we have 2 sine x plus 1 is equal to 0, which gives us sine x is equal to negative 1/2. So the arctan of this would be 7 pi over 6 or 11 pi over 6. So now our second factor to 0, we have sine x minus 1 is equal to 0, which means sine of x must equal to 1. The arctan of 1 would be pi, arcsine of x would be pi over 2. So its 3 solutions for this equation would be 7 pi over 6, 11 pi over 6, and pi over 2. Here we'll be using our double angle identities to rewrite the following trigonometric expression. The first one we have is 6 sine x times cosine x. Since here we have sine x times cosine x, we could possibly rewrite this as sine of 2x. We know the sine of 2x would be equal to 2 sine x cosine x. So to get back our 6 here, we need to multiply this by 3. So this becomes 3 times 2 sine x cosine x. 2 sine x cosine x, as we said before, is the sine of 2x. So this becomes 3 sine 2x. Similarly, in this example, we have sine x cosine x. We can rewrite this as sine 2 sine x cosine x. Now to maintain the 1 here, we would have to multiply this by 1/2, since 1/2 times 2 will give us 1 sine x cosine x. Now we can rewrite this as sine of 2x with our 1/2 as our coefficient. In this example, we could use our distributive property, so this becomes cosine squared x minus sine x cosine x plus sine x cosine x minus sine squared x. Here we can see that two middle terms will cancel, leaving us with cosine squared x minus sine squared x. We know this to be the identity for cosine of 2x. So here we have used our double angle identity to rewrite these three expressions. Here we're being asked to find the exact value of sine 2u, cosine 2u, and tan of 2u using the double angle formula, and we're given that the cotan of u is equal to the square root of 2, and we're also told that u is between pi and 3 pi over 2. So this information here tells us that we're in the quadrant 3. We know cotan, tan is equal to opposite over adjacent, so cotan is adjacent over hypotenuse. So here we have our adjacent being square root of 2, and our opposite is 1. Using our Pythagorean theorem, we can find the hypotenuse, which is this squared, which gives us 2 plus 1, and the square root of 2 plus 1, which is 3, is the square root of 3. So now we have all three sides of our triangle. So we can go proceed to find sine 2u, cosine 2u, and tan 2u. We know the sine of 2u is equal to 2 sine u, cosine u. So this becomes 2. The sine of u would be the opposite over the hypotenuse, so it's 1 over square root of 3. And because it's in the third quadrant, we know sine is negative, so this will be negative. Cosine of u, the adjacent over the hypotenuse, so this becomes the square root of 2 over 3. And this is also negative because cosine is also negative in the third quadrant. When we simplify this, the sine of 2u is equal to 2 radical 2 over 3. Now we can proceed to find the cosine of 2u, which is equal to the cosine squared u minus sine squared u. We already established that the cosine of u is equal to negative square root of 2 over 3, and that the sine of u is equal to negative square root of 1 over the square root of 3. So if we square this, and we subtract them, we get 1/3. Similarly, tan 2u is equal to 2 tan u over 1 minus tan squared u. Tan is equal to the opposite over the adjacent, so this becomes 1 over the square root of 2. So now we have 2 times tan u, which is 1 over the square root of 2, all over 1 minus 1 over the square root of 2 squared, which simplifies to give us 2 radical 2.